Hello everyone, welcome back. In the last lecture, we were talking about the scientific problem in nanophotonics. So when we have a distribution of permittivities in certain region of space, how do we solve for the electromagnetic response? And I mentioned that this essentially involves solving Maxwell's equations. But how do we solve that? So to do that, we have to essentially solve the wave equation. So if you look at the Maxwell's equation, the curl equations here, you have two of these curl equations, curl of H and curl of E. And when you combine these two, you get what is known as a wave equation. This is a wave equation for free space. Okay, so how do we get this equation? So since this is a central part of nanophotonics, I would like to take a little bit of time, try to derive this. So you might have already done this, but I just want to go over this one more time so that you are familiar with the assumptions that we are making and what is the role of each term. Okay, so all of you definitely are familiar with wave equation, which is of this form. This is essentially a second order partial differential equation. So you have the second derivative in time. This is a second derivative in time. And sorry, I have my students here, so they're asking me questions. So let me, what is this?
It should be dou square h by dou t square.
Well, why should it be H? It can be electric field as well. You can have the electric, okay. So the wave equation has two forms. One is the wave equation in terms of electric field, and the other one is the wave equation for the magnetic field. So you can have either of these two things. We can derive them. So it depends, So what I'll do today is I'll derive the wave equation for the electric field, and I'll leave it as an exercise for you to derive the wave equation of the magnetic field. You can do that, okay? And it will be similar in form. So that's a nice exercise. Thank you so much, Sahan. So we have the second derivative in time on the right, and we have the second derivative in the space. So this is a Laplacian operator, which is essentially dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is a Laplacian operator in the Cartesian coordinates. So the wave equation essentially relates the second derivative in space and time. So through the velocity term. So I leave it as a small exercise for you to check that the dimensions match out. So the coefficient of here is going to be the velocity term. Okay, this is a wave equation. So how do we get this wave equation? So we will start with the curl equations given by Maxwell. And we'll also make an assumption that the magnetization is essentially 0. So we'll only take B is going to be mu naught H. Okay, this is the assumption we're making. So with that, I have curl of E, which is given by the partial derivative of B with respect to time, and that will be minus the partial derivative of the magnetic field with respect to time. The second equation is simple enough. So what we'll do now is we'll take the curl of the first equation. So let me take curl of A. So what I want to do is take curl. So I assume that you have gone through a course on vector calculus and you know what curl, divergence and all mean. If not, I would encourage you to take it because these equations, vector calculus is very fundamental to a lot of areas of engineering. So you should take, it will be just a month-long course on vector calculus. You should take it. There'll be a lot of resources that are available in that context. So let's consider curl of the first equation. So I have curl of E. So I'll take a curl of that, and that on the left-hand side. So that will give you on the right-hand side minus mu naught. I'll take the derivative out and I'll say curl of H, right? So I know what is curl of H from the second equation, the B here. So that will be equal to mu naught. Since this is, okay, let's take the second derivative. So mu naught, second derivative of d with respect to time plus the minus mu naught. The first derivative of j with respect to time. So this is there should be, instead of a plus, it should be a minus here as well. So this is what you get, right? And you also know that from the constitutive relations, we know that d is equal to epsilon naught E plus polarization P. So we can substitute and expand. So what you'll end up getting is minus mu naught epsilon naught dou square E by dou T square minus mu naught dou square P by dou T square minus mu naught dou J by dou T. So you already see that the left hand side, we are already seeing that, second derivative in terms of the time, second derivative of electric field in terms of time, that we see on the right hand side of the wave equation. Okay. In addition, we have the few other terms. Okay. So how do we look at this? So we'll put it back together instead of in my handwriting. I have typeset it here. So essentially curl of E is this term. Okay. And to simplify the left hand side, we will use a vector identity, which is essentially given by this. So the curl of vector field will be given by the first term consisting of divergence of the field, and the second term consisting of Laplacian. So it turns out that if you are talking about free space or a region of space where there is no free charges, so this rho f means free charge. If there are no free charges, then rho f is 0. And also if the epsilon doesn't vary significantly over the wavelength scale, then you can actually consider divergence of E to be 0. Because of that, we will be able to simplify the equation to this form on the bottom here. So you see that you have the familiar part, which is the Laplacian on the left hand side and the second derivative of electric field in terms of time, but there are a couple of other terms. Okay, if you consider, let's say, free space, okay, by which we mean there are basically there is no polarization, and also there are no free currents. J is 0 or 0 in free space. If you consider this scenario, the equation reduces to Laplacian of E is equal to mu naught epsilon naught dou square E by dou T square. Okay, and the solutions to these this equation are essentially what are known as plane waves. We will talk about them in a little while, but figuratively the solution is going to be like this. Now you have the electric field which is confined to a plane and it oscillates as a function of time, and magnetic field will be perpendicular to that. So you have electric field and magnetic field which are perpendicular to each other, and they are both simultaneously perpendicular to the propagation direction. So this is what we call as a plane wave, which is a solution of the wave equation, and we will see that. We will study a little bit more detail in the coming sections. But okay, so what is the speed of this wave, right? How fast does it propagate? So for that we have to compare the coefficient of the time derivative. So in the original case we had 1 over v square, right, velocity square, and in the equation that we solved, we got mu naught epsilon naught. So if you can define the velocity of a wave in terms of velocity of the wave or of the EM wave is going to be 1 over root of epsilon naught mu naught. Okay. And if you look at the terms, we mentioned what is epsilon naught and what is mu naught in the earlier lecture. You will see that if you compute these numbers, you will end up getting equal to constant c, which is 3 into 10 power 8, the speed of light. So whenever you have electromagnetic waves propagating in vacuum, we have the speed with which they propagate is known as the speed of light, which is dependent only on the fundamental constants, permittivity and permeability of free space, right? So this is speed of light. So this is how electromagnetic wave propagates. Okay, this is the solution of a wave equation. Now what happens to, let's say, regular medium? Let's say I take a piece of glass. How does the electromagnetic wave propagate in that? So if you go back and look at the original equation here, what would change when you consider glass? Okay, will glass have any currents? No, because glass is insulator, it cannot conduct any current. So we will put the J term to be 0. What will happen to the P, the polarization? Will there be a polarization when you consider glass? And if you look back, you'll recall that glass can actually have some polarization, right? We said the polarization P is given by a certain susceptibility epsilon naught chi times E, right? That's what we did in the last lecture. So we have to consider polarization. We cannot make it 0 now. What is the impact of this? Okay. So if I substitute for P, I'll get mu naught epsilon naught chi dou square E by dou t square. Okay. So now what I can do is I can take the right hand side and I can take common terms out. So right hand side of the equation, I'll take let's say epsilon naught mu naught, and this is 1 and the second term has a chi, so I'll take 1 plus chi dou square E by dou t square. And this particular term we've already introduced, which we call as relative permittivity. Okay. So what this is telling you is the wave equation has a similar form to that of vacuum. If you take a wave equation in, let's say, any dielectric media, it has the same form. Only addition is that you have this additional term of relative permittivity. So what does it imply? What does the presence of permittivity show us? Well, we said that the coefficient is related to the speed of the wave. So in the previous case, we said the coefficient was 1 over mu naught epsilon naught. But if you have a wave in a medium, in a dielectric medium, what happens? Well, the velocity now is modified. It's no longer going to be c, but the velocity is going to be c by root of epsilon r. Okay, and more commonly this is known as root of r is denoted by refractive index n. Okay, so this is the refractive index. So when you have electromagnetic wave propagating in a medium, any dielectric medium, these are simple dielectrics, okay, which let's assume that they don't have any losses. We will get into that in the next week. When you have a simple dielectric, the wave essentially slows down. And the ratio of the speeds is a refractive index. Okay, this is a simple first approximation of what happens. And I must also emphasize that we have made some assumptions. When I said P is going to be epsilon naught chi times E, this is a simplifying assumption. The reason is there are some materials which are anisotropic. That means the way a wave propagates in the one direction, let's say x direction, the speed with which it propagates is going to be different from the speed with which it propagates in the y direction. There are some examples like calcite, okay, where they have an anisotropic response. If you have an anisotropic response, then we have to actually consider polarization in a slightly more complicated form. So now, in this case, the polarization, the susceptibility is not going to be a scalar. The previous case, the susceptibility was a number. But when you have a anisotropic medium, we'll have to consider what is known as tensor. So you have scalar, which is simple number, a vector, which is an array of numbers, and then the higher form of that is what is tensor, which is basically a two-dimensional, it's matrix. Okay, that's why I represent IJ. So it's a matrix of susceptibility numbers in various directions. So we call it a tensor, and then we have to compute. Okay, it's much more involved. We will not get into it right now, except when I talk about metamaterials, I will talk about the anisotropic response. Okay, the other assumption I'm making is that we are dealing with linear medium. What do I mean by linear? Well, it turns out that the P, which is a function of E, linearly dependent on E, is an assumption. You can have higher order terms. The polarization will also be dependent on the square of the electric field and the cube of the electric field. It can happen, and so on. It can have higher order responses. And these are what are known as non-linear responses. Okay, and this leads to a lot of interesting effects. So for example, here, this is a second order susceptibility. And this is a third order susceptibility, and so on. And the presence of the second and third order susceptibilities can actually lead to very interesting effects like harmonic generation and so on. There's an entire field of nonlinear optics which I think probably had a few Nobel Prizes in that domain, which is based on this higher order responses. Right. So in this course we will not really get into the nonlinear phenomena. So what we will do is let's look at that, the dielectric constant, right? Or rather the refractive index in a little bit more of detail. So in the previous slide I said it's the ratio of the speed. It seems like, okay, we are all familiar with refractive index of glass being 1.5, silicon being 3.1 and so on. But it turns out that the refractive index is not a simple number, but it exhibits a dispersion. The technical term we use, dispersion, which essentially means that we have the refractive index, which is a function of wavelengths. Okay. So on the x-axis, I'm showing you function, or rather x-axis you have the wavelength. On the y-axis you have refractive index. So what you are seeing here is various materials and their corresponding refractive indices, and immediately you see that the refractive index is a kind of, it shows a variation. Okay, it depends on the material. There are some materials where it's more or less constant, and then some others which is not. Now, for example, on the top here, the blue is germanium. Okay, and germanium has a refractive index of about 0.8 eV. The green is gallium arsenide, which has a band gap. It's not refractive index. I'm sorry. Germanium has a band gap of 0.8 eV, and the gallium arsenide has a band gap of 1.42 eV. And similarly, if I come down, if I look at gallium nitride, which has a band gap of about 3.4 eV. And finally, you have silicon dioxide, which has a band gap of Eg of GaN. This is Eg of SiO2. Okay, which is about 9 eV. And what you see is the band gap changes as a function of, the refractive index is inversely related to the band gap. Okay, so this is a interesting observation, and why does this happen and so on, we can talk about it in the subsequent lectures. Okay, so I just want to leave you with a thought. So generally when I talk of optics or photonics or electromagnetics, we think of it as a separate domain, and it's sometimes scary because there's a lot of mathematics involved. But I want to underline the unifying or the similarity between various domains. For example, optics or electromagnetics is really very closely related to the electronics that many of you are familiar with. If you look back at how the electromagnetic waves are generated, you must have heard about antennas which generate electromagnetic waves. We will consider that in a little bit of detail. We will show a few things about that in the down the line. But right now, if you have electric charges that are moving, they produce electric fields. So essentially, motion of charges, electrons, give you light, the light generation part. And analogously, when you have an electric field incident on a material, it is going to make the charges move. The electric field in the light or electromagnetic wave will make the charges move, and that is light detection. So you see that the electrons and the photons are very intimately related. They're not completely different domains. They're related by some very fundamental physics. Here I'm listing out a few parameters to just emphasize this. You must have heard about the wave particle duality, right? So you can treat electrons and waves, as electrons and photons, as waves or particles. Okay, both are valid, and there are certain regimes where particle picture is useful, and certain other regimes where the wave picture is useful. So what you see is here, let's say energy. I tabulated a few things for electrons and photons, and you see that the energy of electron is essentially given by p square by 2m. So it's related to square of momentum, and this is called the parabolic dispersion. If you are familiar with electronics, you must have heard about the parabolic dispersion for electrons. Whereas if you come to photons, the dispersion is slightly different. It's a linear dispersion. The energy is linearly related to the momentum. Okay, and similarly, momentum, you have mv, mass into velocity. This is a classical picture. If you look at the quantum picture, it is h cross k. And similarly for photons, you can talk of momentum in the quantum picture, which is h cross k, or you can also define in terms of de Broglie wavelength, rather h by lambda, which is essentially what de Broglie relation is. And the wavelength, of course, you can rearrange. So what I want to emphasize is that the behavior of electrons and photons is quite similar. Okay, electrons are governed by Schrodinger equation, which is essentially a second order partial differential equation wherein you have the second derivative in space and first derivative in time. That's a Schrodinger equation. In photons or electromagnetic waves, we deal with the wave equation, which is again a second order differential equation, but this time it is second order in both space and time. Okay, that's a slight difference. All right. So this is where I'll stop. I'll take a few questions. Yeah.
How does wavelength or other parameters compare for both electrons and photons?
Okay. Yeah, that was a very interesting question. One of the students was asking about how does these parameters compare? Okay, for let's say electrons and photons, are they similar in range or not? Okay. Well, electrons have much higher, you can accelerate electrons to much higher energies compared to photons. If you take a photon, the typical, let's say, energy in the visible range is going to be about a few eV, let's say 2 to 3 eV. That's in the visible domain, okay? Or even I would say 1 to 3 eV, okay? That is the energy of a photon, okay? Just remember, I'm talking in EV units. It's much more easier to deal with energy in this way. If you talk of joules, you'll have to talk of 10 power minus 19. So I would encourage you to actually try to figure out how to convert between wavelength, various units, let's say nanometers to, EV to centimeter inverse and so on, the various units, and you should be comfortable. Okay, that's easier. It makes your life easier. So the photon energy is typically in 1 to 3 eV. Whereas electrons can be accelerated. For example, I mentioned an SEM. So wherein the energy of an electron can be up to 100 keV. Okay, it can be very high. It depends on how much you accelerate to. Or you can talk of the wavelength. The wavelength of photon in the visible range is about, let's say the center wavelength is 500 nanometers. Whereas the wavelength of an electron can be much, much smaller. Okay. And this has some implications we will talk about when we're talking about the diffraction limit. All right. So yeah, the numbers are quite different, but the underlying phenomena has many similarities. Okay. Similar to, you might have, when you studied quantum mechanics, you might have studied about tunneling of electrons. You can talk of a similar concept for photons, wherein, tunneling of electromagnetic waves, and there is forbidden regions and so on. Okay. So yeah, they are related. Yeah. Anything else? If not, yeah, thank you so much for your attention, and I'll see you in the next lectures. Take care. Bye.